Hello everyone and welcome to the video lecture on module 5 spread spectrum communication. In this module we have these important topics to be covered. The first one being the PN sequence and its generation, where I'll be telling you what is a PN sequence and how are these sequences generated. PN sequence is nothing but a sequence or a string of zeros and ones. I'll be telling you what is the necessity of such a sequence in spread spectrum communication. Above all, I'll be telling you what is spread spectrum communication first. And then we'll be going for the synchronization topic, where we have three main subdivisions to be covered. First is a frame synchronization, then you have symbol synchronization, and the third is chip synchronization. Third and the most important, the spread spectrum modulation techniques, where you have two major types. One is DSSS, direct sequence spread spectrum, and second is frequency hopping spread spectrum, which is further being classified into fast and slow FHSS. So these are the major topics which we are going to cover in this module, and in this video I'm going to cover only the first topic, which is PN sequence and its generation. So let's quickly start with our topics. I'm sure this heading or concept of spread spectrum is very new to you, right? You have not come across these topics in any of your previous semesters as well. So let me give you a brief intro of what is spread spectrum and what is the need for such a technique. Yeah. So previously in all our classes, we had discussed different types of digital communication systems, right? In all these systems, throughout I was talking about two major constraints. One was the channel bandwidth, the other one was the transmitted power. Now if we think about a communication system, let me say these are not the only two parameters which are to be considered in real-time scenario. Now if we look at the first example, if we say for military applications, what are we looking for? In military communication, we always look for data security, right? So whatever data we are transmitting should be secured enough so that an enemy or an intruder should not be able to read our message. So first criteria there is security. Not just intentional interference. There could also be unintentional interference caused by a user who's trying to transmit something using the same channel. So in all such cases, there could be jamming of signals. I'll be telling you what jamming is later on. How is a spread spectrum signal different from a normal signal? From the name itself, we know spread spectrum. So the signal is spread over the given spectrum. Yeah. So here the spread spectrum signal occupies a larger bandwidth than the normal signal. We're going to see how that's going to happen. So before which, let me give you a brief idea about spread spectrum communication model. Yeah, so let's begin the concept of spread spectrum through a simple communication model, which we are already familiar about. So in a communication model, we do have a source, we do have a destination, right? So from the source, what happens? Source goes, for a digital communication I'm talking about, it goes to channel encoder. From the channel encoder, it goes to a modulator. From the modulator, it goes to the channel. So this, let it be the channel. And then you have the demodulator. Then you have the decoder. And then you have the destination, right? In spread spectrum modulation, what we are going to do is, we are going to multiply the signal in the modulator. We are going to multiply the signal using a random sequence of zeros and ones. Now, that random sequence is called as PN sequence or pseudo noise sequence. Yeah. So we need a generator, right, to generate that sequence. So we use a pseudo random pattern generator, some string of zeros and ones. Yeah. which looks like random, which is not actually random, but it looks like random. That is why it's called pseudo random noise. So even so this sequence is being multiplied with the signal over here. Now what happens at the receiver? This is happening at the transmitter, right? So the receiver, the receiver has to know this same pattern to decode the message back to its normal form. This demodulator also needs to know this sequence, the same sequence which the transmitter had used. So the pseudo random noise pattern generator is required at the demodulator as well. The same sequence has to be used, because let me say, for example, if I have to send a message to someone of your class. Let me say I'm trying to convey that her marks. Let me say I'm trying to convey her marks to Ameya. So here I need to convey such that none of you should be knowing the value or the mark what she has attained. So what I do is the mark, let me say if she has scored 45 out of 50. So this 45, maybe I code it to some letter G. Yeah, so this is a code used. For 45, the code uses G. So I'll be transmitting only G to her. So she has to know in prior that G stands for the value 45. So this is a code and this is the actual value. So the pseudo random pattern generator is nothing but something similar, where the code is to be known by both transmitter and the receiver. Yeah. So this is a basic model of spread spectrum communication. Now let's move on to what is a pseudo noise sequence. This module is not so complicated. I would say my opinion is, compared to all other modules what you have studied, this is much simpler and a smaller one, and you'll find it little interesting as well. So pseudo noise sequences. Or PN sequence. In short, we'll be referring it as PN sequence, okay, throughout the module. So PN sequence generator. How do we generate? As I told you, a PN sequence is nothing but a string of zeros and ones, right? So how do we generate the sequence? We basically use shift registers to generate this PN sequence. Let me just draw a simple figure of its generation. I have a parity generator here. Yeah, so parity generator, and you have flip-flops. We have already learned what a flip-flop is and all that. So here the output of parity generator is given. We use D flip-flop here, Q and Q bar, right? So output of parity generator is to be given to the first D flip-flop, and then output of the first to the second, D1 and Q1, and similar way. You have so many number of this is general picture. Yeah, so you have dm number of flip-flops. This is the output. So, and for each flip-flop you need what? You need clock, right? So we are providing the clock over here, and then each output of the flip-flop is being connected to the parity generator. This is the figure of a PN sequence generator, where we have the parity generator, we have D flip-flops, M number of D flip-flops, clock is being provided, and output of each D flip-flop is being connected to the parity generator inputs, and the output of parity generator is connected to the first D flip-flop. Yeah. So here, what is a parity generator? I'm sure you might have heard about this parity generator before. Yeah. So parity generator, it generally consists of XOR gates. Yeah, XOR operation. I hope you know the truth table for it. Yeah. How is it? 0, 0, let A and B be the inputs. 0, 0, 0, 1, 1, 0 and 1, 1. How are the outputs going to be? 0, 0, 0, 1, 1, 0. Right? So we can say when both are zeros or both are ones, that is even number of zeros, even number of ones, you have zeros, odd number of ones, you have 1. Yeah. So this parity generator gives me an output of logic 0 when parity generator output is 0 when an even number of inputs are at logic 0. What are the inputs to the parity generator? Nothing but the output of the flip-flops, right? So when even number of flip-flop outputs are connected to parity generator, then you have a logic 0. When odd number of inputs are connected to the parity generator, you have a logic 1 output. So remember this, because it's XOR operation. You have parity generator is nothing but XOR gate, and whenever the inputs connected, the number of inputs connected to the parity generator is even, then you get a logic 0 at its output, and whenever it's odd, you get a logic 1 at its output. Yeah, and each flip-flop, depending on the clock, the value keeps changing. So this is the basic understanding about the PN sequence generator. And however, in this figure, if you check out, this is not really random, right? If we know the pattern, what is going to be the next output, if you know the previous value, you can predict the next value. So you cannot completely call it random, because the sequence is, the figure or the structure is deterministic in nature. So that is the reason, though it looks like random, when you generate a sequence of 1, 0, 0, 1, 1, 1, 0 and all that, this looks like random for us, right? But it's not really random. After some period, the same value starts repeating. Yeah, so it's predictable. That is the reason, though it looks like random, it is not actually random. That is the reason we call it pseudo-random sequence. Yeah. So next, now to make this sequence look like truly random, what we do is we increase the size, or we increase the number of bits. Let me say if I am using a 15-bit sequence, so many zeros, ones and all, this, if you look at it, it looks like truly random, nothing is repeating. Yeah. So it generally looks like a random signal. That is how we make it look random. We increase the number of, or we increase the length of the sequence. Now the maximum length of a sequence can be considered to be, if there are m number of flip-flops, the maximum size or the maximum length of the sequence that can be generated is 2 raised to m minus 1, where m is the number of flip-flops. Maximum length sequence, or we call such sequences maximum length sequences, okay? Or the maximum length sequence is a code which represents a commonly used periodic PN sequence itself, but with the maximum length. Yeah. Now with increase in m, when m increases, what happens? M increases. And what about the period of the signal? So n is also, this is nothing but n, the period of the sequence, or the length of the sequence. Yeah. So when m increases, obviously n increases. Yes. So what happens when n increases? The sequence becomes random. Sequence tends to be more random in appearance. Though it's not actually random, it more of, it looks like a random sequence. Now moving forward, let's look at the properties of these maximum length sequences. We have 3 main properties which you have to cover. Properties, once you understand, it's interesting, and you can easily put it down in your papers without much of a reference to your notes. Yeah, the first three, we have 3 properties. The first property is balanced property. Second property is the run property. And the third, these are important properties of PN sequences, has been asked in the previous university exams question paper. So one is balance, second is run, and third is correlation property. Correlation property. So we'll look at each of these in detail. First, balance property. So balance property, what it says is, in each period of a maximum length sequence, the number of ones is always one more than the number of zeros. Let me repeat it, or let me tell you what it actually means. In a period of a maximum length sequence, we know the period is n. So in the length, length of the sequence. Within the length of the sequence, the number of ones, if you count the number of ones, it will always be one more than the number of zeros. Let me take an example to explain this property in a better way. Let's consider a sequence, let's say 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. If you consider how many bits are there? 4 plus 3, 15, right? So you have the length is 15. In this, if we count the number of ones, how many ones are there? 4 over here, 5, 6, 7, 8. Yeah. So total length is 15, and out of which how many? 4, 5, 6, 7, 8 number of ones. Yeah. And how many number of zeros? 1, 2, 3, 4, 5, 6, 7. 7 number of zeros. So which is 1 more than number of ones, right? So that is the first property which says number of ones will be 1 more than the number of zeros. Here we have 8 number of ones, which is 1 more than the number of zeros. Yeah. So this is the first property. Next property is run property. In run property, what it says is, the sentence or this statement is little lengthy. Let me just read it out for you. Among the runs of ones and zeros in each period of maximum length sequence, 1/2 of the runs of each kind are of length 1, 1/4 are of length 2, 1/8 are of length 3, and so on, as long as these fractions represent meaningful number of runs. So that is a statement. Let me tell you what it means. Let's consider the same sequence. 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. Yeah. According to this property, what it says is, among the runs of ones and zeros. Now what is a run? Run is nothing but, it's a string of continuous values. If you consider this sequence, continuous values when it comes, this is a run. 1, 1, 1, 1. Now next 3 zeros in continuous. This is run. This is also a run. Here there's only 1, right? Next is 0. So this 1 itself can be considered as a run of length 1. This is a run of length 4. This is a run of length 3. This is of length 1. This is of length 2. This is another run of length 2. This is a run of length 1. Again 1. And this is also 1. So you have 1, 2, 3, 4, 5, 6, 7, 8. Total runs you have 8. Now, in this total number of runs, if you check out how many runs are of length 1. This is of length 1. Yeah. Then this is of length 1. This is of length 1. This is of length 1. So 4 out of 8 runs, 4, which is nothing but half, right? Half of 8 are of length 1. Yeah. This is what the property says. Half of the runs are of length 1. 1/4 are of length 2. If you check out the length 2, this is a run with length 2. This is also a run with length 2. You have 2, right? So 2 out of 8, which is nothing but 1/4 of 8 are of length 2. Now consider length 3. 1, just 1, right? Which is nothing but 1/8 of 8 are of length 3, and so on. So this is run property. Now if I read out the statement again, among the runs of ones and zeros in each period, 1/2 of the runs of each kind are of length 1, 1/4 are of length 2, 1/8 are of length 3, and so on. That is run property. Third property is correlation property. So correlation, that is autocorrelation I'm talking about. This property states that autocorrelation of a maximum length sequence is periodic and binary valued. That is a statement. Now autocorrelation is something familiar to us. We talk about autocorrelation function. How do we represent it? R of tau is, how is the formula? 1 by t. This is what you have already learned. Minus tb by 2 plus tb by 2 c of t minus tau dt. Now if you solve these equations considering the signals which we already covered in the module 1, right? So autocorrelation function, if you solve it, r of tau is equal to 1 minus n plus 1 by n tc for tau less than tc, and it is minus 1 by n elsewhere. So if you solve this, simplify this integral part, you will get this value of autocorrelation. Now if you plot this function, how are you going to get it? If you plot it, we are going to get it as, this way, where this is 1, this is r of tau, you have minus 1 by n over here, this is ntc, this is minus ntc, yeah, this is minus tc, this is plus tc. Now if you plot this equation, you get this kind of a signal. Yeah, this is r of tau. Now if you consider the power spectral density, isn't this periodic function? So if you plot the power spectral density of a PN sequence, if you plot the power spectral density of this sequence, how do we get it? We get it this way. If you sample it, you get it this way. This is S of f. That is power spectral density of the signal in terms of frequency. Power spectral in terms of frequency. We plot it in frequency domain, right? So this is the plot for autocorrelation function, which is periodic, and it is a two-valued function. So these are the three properties of maximum length sequences. Let me just rewind. That is balance property, run property, and correlation property, autocorrelation. Alright, so we are done with the topic of PN sequence. The next topic would be covered in the upcoming video, next video. So let me just quickly recap of whatever we have covered in the video. So I told you what is spread spectrum, which is nothing but spreading the signal in the given spectra, and it's done to get security of signals. And we also looked at why a PN sequence is used, where it's nothing but a code which is being multiplied with the signal, and then and the signal or this code is to be known to the receiver as well. And we looked at different properties. So thank you for watching the video. I hope the topic is clear to you. Meet you in the next video. Thank you. Bye-bye.